Hello and welcome to another episode of Risky Business. Last time, we started writing a PWM speed test, which, by the way, is on GitHub. And I don't remember if the PWM speed is specified in the documentation or not. We looked for it a little bit, I believe, and we didn't find it, so we decided to write a test. We could also just ask on like the SiFive forums or something. But I felt like it was time to do a little bit of actual experimentation ourselves. And I'm pretty sure it just uses like the external timer. But we're gonna find out through experimentation. So yeah, I have on the Risky Business GitHub, this you don't need to back me on Patreon to have access to. Everything I do on the Risky Business show will be available on here. So for example, there's also our Milton fork on here, and the annotations that Miblo does are in here as well. But I put the PWM speed test here. You can see I committed day 49 and 50. And of course I renamed it from just test to PWM speed test. And you can see the code here. Obviously right now, if you actually wanted to try this program, it would just like brick your Hi-Five 1. Not really brick it, but you know, you need to go into recovery, the safe boot, and then reflash it from there. But we figured out that we need to take a look at entry.S, I believe. And that was one of the things on our list of things to do anyway. We see it right here. To do, dive into entry.s. So we're going to do that. And so I think I've rebooted since last time I've done an episode, so I don't have any of the code up right now, but we will rectify that right now. So we're going to go to Programming, Freedom SDK. Now let me see here. Let's start opening up the stuff we want to look at. So there's going to be a lot of stuff we want to see here. Okay, this has got to have pretty much everything we want, right? Is there an entry.s in there? I see a v entry.s. There's an entry.s, yeah. So this has pretty much got everything we want right here. One thing I might add to this, well here, I'm just going to open this up and jump to entry.s. Okay, so here's entry.s, and we're going to study this in detail. But I also want to go to the Freedom SDK, the BSP folder, and I just want to run a diff on entry.s and the one for RD, because the code we were looking at previously that prompted us to start writing a PWM speed test, I remember the code we were looking at was for the RD. So I just want to know, is there a difference in that entry.s? So it looks like the entry.s for the RD is not in that folder. It must be Coreplex. And we would be doing E31. I'm very excited for the... Oh, it's not there either. Where is the other entry.S? There is a different entry.S, isn't there, for the RD? Maybe I'm wrong about that. I was thinking there was... Maybe not. Maybe not. So let's just assume at this point that there is a single entry.s for both, and there's no difference. I was going to see if there was any difference between the HiFive1 entry.s and the RD devkit entry.s, but it appears they might be using the exact same file. So in that case, there's nothing to diff. Okay, so we're going to read through this and understand everything, and then we're going to add it to our own project. So first of all, in entry.s, a .s file is an assembly file. So this is RISC-V assembly instructions in here. I think this is using the GNU assembler because it appears we've got some C stuff in here. We've got an if not defined entry-s, define entry-s, and then we have a couple includes. We're including encoding.h and SiFive bits.h. So we might want to take a look at those files too, I guess. But yeah, that's like, and of course there's a C style comment as well, but we see this is assembly file. So we have section text entry, align to global trap entry. So I'm not too familiar with GNU assembly to be totally familiar with this stuff, but text entry would be where the code lives, like that's the section of the executable where the actual code lives. And again, we haven't taken a look at the format that these our code gets compiled to, like the actual executable format. But I'm assuming on the HiFive1 with bare metal, the text section of the executable is just the very first thing. I don't think there's like a header. I don't think it's like an elf file or anything like that. I'm pretty sure it's just like just the code in a file and like data at the end, something along those lines. But I suppose this would matter if we're doing like for compiling an ELF file for Linux or something like that, then this would be relevant. So I guess it makes sense to put it in there. I don't know what the align to is for. And then we have global trap entry, but we see like the trap entry label right here. So I'm not sure why there's, like, I guess this is saying in the global like symbol table to put a trap entry symbol or something like that. I'm just guessing here. But here we have the label, and then we're gonna get into the actual good stuff that we care about, the actual code. So, okay, and then here's the endif for the header guard. And then again, .weak handle trap, and then here's the label. I'm not familiar with what this is. And then there's a, it looks like a number label. Is that what that is? And then we see this is jumping. So is this jumping 1B? Is that saying jump just like to itself or something? I feel like this is just like a placeholder handle trap that spins, but I might be wrong. I don't understand what's going on here. But I remember the actual code looked pretty straightforward. So like here, we're adding to the stack pointer, so we're just bumping the stack pointer to, which essentially is just allocating memory on the stack, right? And we're allocating 32 entries, right, for the 32 general purpose registers. And we see that we store all of them. So we don't bother storing x0 because x0 is hardwired to 0. That is the 0 register. But we store x1, x2, and so on and so forth, all the way to x31. And those are just the names for the register file, the various integer registers. And we see it storing them sequentially, like on the stack. So that makes sense. The reg bytes is obviously the length of a register. So the HiFive1 is a 32-bit chip on it, the FE310. So this is moving in 32 increments is what we're doing here, and that's why I say there's 32 entries that we allocated space for. 32 times the number of bytes per register, so that's 4 bytes per register, right? And it's negative because the stack grows down. So at least I'm assuming the stack grows down on here like on a normal Linux system, Presumably we're doing the same on the HiFive1. So if we're adding a negative to the stack pointer, right, that's the same as subtracting. So it bumps the stack pointer to a lower address in memory, which is growing the stack, because that's how it grows in memory, is it grows down. Like the addresses get smaller as you allocate. So hopefully that's clear why it's doing negative 32 times reg bytes. I think I explained that pretty well, and I'm confident that I'm understanding that correctly. And so this all makes sense, right? I'm pretty sure I don't need to explain more about what this is doing, right? It just stores all the registers onto the stack in the space that we just allocated. And then, so we read a few things from the CSRs, the mcause register and EPC. So I mean, mcause is the cause of the exception, right? Or, I mean, the cause of the interrupt. So it could either be, like, it could either be basically like a hardware exception or a proper interrupt that caused it. And then EPC, I'm gonna need a refresher on that. And we're saving the stack pointer in A2. We call handle trap. And then again, we're doing some stuff. So let's start by taking a look at each of these instructions here. I think this is the place to really start studying. But just to skip over that to review again, after we do this stuff, we restore all the registers. So we put all the registers that we stored on the stack back into their appropriate registers from the stack. And then here you see this time it's positive 32 times reg bytes. So we're deallocating the memory we allocated on the stack to deallocate that memory, and then we return. All right, so again, just to give a little bit of context here for people who maybe don't know about like how the stack and the heap and all that are laid out in memory. Basically, your process gets an entire address space, like it sees an entire address space. And on Linux, that's of course virtual addresses that it sees. So like it sees the entire address space, but it's not actual like physical memory that it's seeing. It's virtual addresses. And so when you go to actually allocate memory from the system, you know, you request the, like, I need to use a page of virtual memory, and then it actually goes and maps that to a physical page in memory. And so in C, we're used to thinking about the concept of a heap and a stack, but really those are just like constructs of the language if you think about it, because it's really just, you know, an address space. And in that space, we say we start the heap at a certain location and we start the stack at like the other end, basically. So like maybe I guess the stack we would say starts at a very high address in the address space, whereas the heap starts at like a low address, and then the heap grows higher and higher in memory, higher addresses, while the stack is growing down. It's growing lower and lower in addresses. And so unlike Linux, you have like the break and S break instructions, I think. Or not instructions, system calls. So like man, is it 2 BRK? Yeah. So here we see the syscalls for adjusting the break, the program break as it's called, which is how the lowest level, like, unless you're talking about memory mapping files, which is different, but the lowest level way that you manipulate the heap is actually basically the same as the stack. You just bump a pointer. So you have this pointer to where the heap is at, and to allocate memory, you just, you know, bump that pointer, and that's basically what the break and the S break system calls do. So what's the difference? I never remember the difference between the two. Break says the end of the data segment to the value specified by address. sbreak increments the program's data space by increment bytes. So that's the difference between the two. And you can implement one in terms of the other, of course. But that's the lowest level building block that general purpose allocators are built from, generally speaking. But like I say, there's also like memory mapped files and stuff like that. But for the stack, what you actually have is in the hardware, you actually have a register called the stack pointer, which is, in our case, actually called SP. Like on x86, x64, you'd have like RSP or ESP, I think, something like that. Depending on the naming on x86 depends on the width. So like if it's 64-bit, I think it's RSP, and if it's 32-bit, you call it ESP, something like that. But on RISC-V, we just call it SP, and it's one of the registers we have. And I think that's an ABI name. So on RISC-V, a thing that's different about it is there is two different naming schemes for the registers. Like we talked about how there is X1, X2, X3, so on and so forth. But there's also the ABI names. So I think the stack pointer is actually one of these registers. Same with, we see here it's talking about A0, A1, A2. Like those are just some of these registers in here, right? There is some of these, but it's a different name to refer to the same register. So I wonder what is the most convenient document to see the different register names. I'd imagine this one right here, right? The user level ISA. Registers. You'd think it would be like the first thing. Let's just go to overview. Like you'd think they'd specify those right away, wouldn't you? Okay, well here's the registers, but it just has the X names. I want to see the ABI names. Like a comparison of... So maybe this doesn't have them. Maybe it's... Would that be in the privileged spec? It's got to be in one of these documents somewhere, right? I'm pretty sure it would be in one of these. Well, let's search for the stack pointer. How about that? You know, that's going to hit a lot of things like spec. Let's search instead for A0 or A1. Like here we see we're using it, but So they have examples in the code where they use that naming scheme, but they don't. Here we go. Well, here's some of them. So this is in the compressed instructions. It has a few examples. So apparently A0 is x10, A1 is x11, A2 is x12, so on and so forth. But where's a full listing? Oh, here we go, maybe. Okay, so SP, the stack pointer, is x2. And this is like a random table in talking about floating point. Let me see here. I have updated links.risky.tv. And one of the things that I added here, so I changed it up. Originally on specs, I had a link to like each of these documents that we're looking at, but I changed it to just link to the SiFive documentation page because they have like a sidebar on the left here where you can see, and I guess they have them all listed right here too, and you can see that there's a ton of different and this is only going to grow in time as they add more. Like when we get the development board for the E51, which is something I'm really excited about. I don't know if you guys have been following this stuff, but SiFive has announced that yeah, they announced the U54-MC Coreplex IP. It's a RISC-V 64-bit quad-core processor with Linux support. So this is very exciting to me, right? This is what we've been waiting for, and it's coming down the pipeline already, and we're still like just getting our feet wet with the Hi-Five 1, and they're already coming out with this. So it should be like early next year, I believe, that we're going to be able to get a development board that so like the Hi-Five 1 basically, but it's going to be with this chip on it, and that is super exciting because we'll actually be able to play around with a beefier system that can run Linux. So it uses the RV64GC ISA, and G is just shorthand for like I am a FD, I believe. So integer, multiplication, atomics, floating point, single and double precision. And of course the C is compressed instructions. So that's going to be really exciting. And let's see what they say here. It's got 32 kilobytes instruction cache, 32 kilobytes data cache, runs at 1.5 gigahertz. It uses 28 nanometer technology. So this is like really exciting. Okay, here we go. Development board is going to be available Q1 2018. So early next year, sometime, first quarter of next year, we should be able to get our hands on a development board, and that's going to be super exciting. So what I really want to see is someone take one of these chips and stick it on like an ATX board, right? um, I suppose you would need to modify it to like have the PLIC supports PCIe and stuff like that. I think you might actually, if you want to take one of these chips and like get a proper ATX motherboard with it on it, it would have to you'd probably have to do some modifications to the chip design to support things like PCIe. But like yeah, a company could license their Coreplex IP, the U54-MC Coreplex IP, which is their business model, SiFive's business model, right? You could go, if you have a company, you could go and license this and make whatever modifications need to be made, stick it on a ATX board, and then sell the board. So, you wouldn't have to, I don't think you would really need to make like a socket. Like, just having it on the board, integrated on the board, like I would buy that and make a little rig out of it. you know or like if you put it in a laptop, if someone made a laptop using one of these, that would be really cool too. But I mean, if we're talking a quad core at 1.5 gigahertz, like that can do pretty much like everything I would need it to do. Like maybe that's going to be a little bit too low. I don't know if it would be fast enough at 1.5 gigahertz to do all of like the streaming kind of stuff that I do personally. But I'm really excited for the day we get a RISC-V desktop, right? That's what I want. I want my work machine that I do all of this stuff from to be a RISC-V machine. That's my dream. But I don't know how long that's going to take. But the big obstacle there, I think, is going to be getting like driver support. Like obviously, you could put it on an ATX motherboard, but then you can't just stick your graphics card in there and expect it to work. The driver would actually need to be supporting RISC-V. But I know, and I know I'm going on a huge tangent here, but Talos workstation. So back before we even knew about SiFive and the Hi5 One and things like that, when I was first considering this project and looking at the different architecture options that are out there, such as RISC-V, and of course I ended up deciding RISC-V was the most exciting thing. And now, of course, we have the Risky Business show, which is all about RISC-V. But another architecture that's out there is the Power architecture from IBM. And this Raptor engineering company has actually like been making ATX boards that have this Power chip on it. So you could actually have like a Power workstation if you went to these guys and paid the money for it. So you can see they have these actual boards, and I guess they sell entire desktop systems now as well. Secure workstation, desktop development system. So like something like this would be really exciting to me if a company like Raptor, licensed the RISC-V stuff from SiFive and did this type of thing. Like that's the first major step to getting like actual working desktop systems that have like all that we want out of them, like getting drivers ported and stuff. a big motivation to doing that work of someone going and porting a driver, assuming it uses assembly, assuming the driver isn't just C and you can just compile it and run it. But like I'd say, a big motivating factor, I think, is going to be having actual hardware where you could, it has a PCIe slot and you could stick a graphics card in there. And then, if you've got that hardware, that's pretty motivational to try to, get the graphics card working with your RISC-V processor. But I feel like it's, maybe something like a RISC-V laptop could be coming down the pipeline before you know it, or maybe a desktop even. Like, this chip is a huge step in that direction, because, it's not comparable to, like, the modern chips we have today, but it's good enough to do a lot of what you'd want to do, and you could put it in like a mobile phone as well, something like that. Like, it's really exciting because you can run Linux on this thing. Like, just look at the specs. Sorry for going on such a long tangent. I'm just geeking out over that. It's very exciting to me. But back to what we're actually doing, I guess we should actually do what I said I was going to do today and study some code. So yeah, we saw the stack pointer is just, it just points to an address, and you just bump the pointer to allocate or deallocate memory. That's how the stack works. Whereas the heap, it has the underlying same kind of mechanism with a program break, but normally we use general purpose allocators built on top of that allow you to, allocate and deallocate arbitrary, like, things aren't necessarily contiguous in memory. So essentially, you can imagine if you were to implement something like that, you just move the break to allocate a bunch of memory, and then you divvy that memory up, just like in the same way that you can create a user space allocator where you request memory from the system using something like mmap or even malloc, just any allocator, and you get a pointer to some memory that you allocated, and then you're free to divvy that memory up however you choose. Normally we just allocate the memory we need for an allocation and use it directly, but you can also just make a really big allocation and then divvy that up throughout your program's lifetime. So like at the beginning of your program, you say, I'm going to allocate a gig of memory, and then through the entire lifetime of your program, you just divvy up that memory that you allocated whenever you need memory for something. And that's what the concept of a user space allocator. And that's why, like, doing something like malloc is more performance prohibitive, I guess you could say. It's not as good in terms of performance as, like, the stack. And of course, the stack has other things going for it, like we have hardware registers for the stack, and typically everything on the stack is going to be in the cache. It's going to be very warm in memory, so you get very good performance there, which I guess you could say is hardware optimization for that particular type of use case of memory. But speaking of user space allocators, just in case you didn't know, let's go to forum.risky.tv just to give a little bit of a shameless plug here. I do have a library. I haven't worked on it in a while. It was 3 months ago that I released the very first version of it. But this is a library that is designed to be building blocks for writing user space allocators. So like I said, if you don't want the slow like performance, if malloc is a performance bottleneck for you, like something that games often will do is they'll allocate memory up front at the start of their, like when the program starts up, they'll allocate memory from the system, and then throughout the lifetime of the program, they'll divvy it up. And because you're writing custom user mode allocators, you can really tune the performance better. So you can have different kinds of allocators for different kinds of allocations where you know the way you're using memory, you can exploit that to get more performance out of it. And you're not needing to do that context switch to Linux, where you switch to the operating system and it does the the system work of allocating memory, and then it hands back to you the user mode program to continue running. Those context switches of doing system calls can be expensive. So there's good reasons why you might want user mode allocators. And my library here, nwrmem.h, is a single file header library that's designed to help you with that. And the only thing I've implemented is a region allocator, which is like the simple bump the pointer kind of stack allocator. And I've implemented a lot of useful functionality for a region. Maybe in a future version I'll get rid of deallocate, because that one is kind of, it works, but it's confusing the way it works, because the signature of the function suggests that it could deallocate arbitrary like chunks of memory, but with a region allocator you can't do that. It's like a stack. You can either bump the pointer back or forward, and if you're bumping it back, you're deallocating memory, and that's what the dealloc is designed to do. But maybe in a future version of this library I might get rid of that, just because it's confusing, and it's simple enough to implement yourself if you really need it. Because like I say, it's basically just bumping a pointer. But anyway, enough of that tangent. So that's basically what a stack pointer is, and how kind of memory works in a system. And now we're looking at these lines here, where we have these general purpose registers A0, A1, and A2. And I think these are setting up for like the arguments to a function. Like when you do a function call in C, you pass arguments into it. Well, in assembly, that needs to translate to either putting things on the stack or in registers. And typically you would prefer to put things in registers. And you'd only go to the stack if it's like a big structure or something. So if you're putting things in registers, the API specifies how you do that, like where you put those things in memory. And so that reminds me what we were doing before I got so sidetracked. I was going to show you... Oh, that's why I opened links.risky.tv, isn't it? Sorry that I'm so out of it. I haven't streamed in a while. But I'm getting back in the groove here. So, let me see here. Oh yeah, so we saw for the specs, this is what got me sidetracked. I showed you that I switched this to the SiFive documentation, just a link to this page where you can find all of their specs. But I also have a link here to the ABI specification. I believe this was linked in one of the blog posts from SiFive. Palmer Abbott, I think his name is, something like that, does a blog for SiFive. Oh, here it is. Palmer Dabbelt. I don't know if I pronounced that correctly, but he's a guy who works at SiFive, and he does blogs as well for the company, the All Aboard blogs. And I believe in one of them he linked this document. So I didn't know about this document until I read that blog post. But I added it to useful links because obviously this is a very useful thing to see. So, okay, so here we see the registers, the ABI names, and the meanings. And it also tells you whether it's preserved across calls. So this is where you should go if you want to know this stuff. Like I said, first of all, I was looking at like here in the user spec and the privilege spec. I was looking for it as well. Probably the better document to go to is this right here. So we see A0 through A7 are argument registers. So yeah, these are for passing arguments to a function, basically. So we're saying the first argument to handle trap is going to be set with this CSRR call. So this instruction is reading from mcause into A0, and this one is reading from mepc into A1, so that's going to be the second argument to the handle trap. And then the third argument is the stack pointer, because we see we're moving the stack pointer into A2, and then we call handle trap. So that's like the function signature, basically. It's mcause, mepc, stack pointer is what we're passing into the trap handler. And of course, we see that the actual registers that we're using here are X10, 11, and 12, right? And let's now take a look at, is it going to be in the privilege spec or is it going to be in the user spec? The control status register stuff. That might be in privileged. I'm going to check user first. Yeah, it must be in privilege, because like this is going to be like IMAC, FP, those types of extensions. Here are naming conventions. Actually, this might... Okay, so some of the ABI stuff apparently is specified here, I guess. Although this is talking more about like the IMAF, like these things, not the actual register naming. So never mind, that doesn't have what I was thinking it might have. So yeah, the privileged has the CSRs. So we're looking for mcause. Yeah, machine trap cause, but I want to see the layouts. And I want to see the CSRR instruction as well. So let's find mcause here. Here's mepc. Okay, that's exception program counter. So what all does that have? So is it implementation specific? Because it says the low bit is always 0. And on implementations that do not support instruction set extensions with 16-bit instruction alignment, the 2 low bits are always 0. So when a trap is taken, mepc is written with the virtual address of the instruction that encountered the exception. Okay, so that's just telling us where the exception happened. So like if you try to execute an illegal instruction, this would tell you what instruction you were trying to execute when the exception got raised. So that's useful for very obvious reasons, I think. I don't know if it would be useful if it's like a proper interrupt and not like a hardware exception. I don't know if you would actually need mepc in that case. But I understand why you'd pass it to the trap handler, because the trap handler needs to handle both cases. And you determine that using mcause, of course. Okay, so mcause has the interrupt and the exception code. So the interrupt is a 1-bit field indicating, so that would indicate whether it's like a hardware exception or a proper interrupt. And then the exception code would indicate more information about what it was, basically. The mcause register is a read-write register formatted as shown. The interrupt bit is set if the trap was caused by an interrupt. The exception code field contains a code identifying the last exception. So there's a table that lists the possible machine-level exception codes. That's what we want to know. We do not distinguish privileged instruction exceptions from illegal opcode exceptions. This simplifies the architecture and also hides details of which higher privilege instructions are supported by an implementation. The privilege levels servicing the trap can implement a policy on whether they need to be distinguished, and if so, whether a given opcode should be treated as illegal or privileged. Interrupts can be separated from other traps with a single branch on the sign of the mcause register value. A shift left can remove the interrupt bit and scale the exception codes to index into a trap vector table. That's smart. Where's the table? So this must be the table for mcause. Machine cause register values after trap. Okay, so here's when the interrupt value is 1, and here's when it's 0. So when it's 1, it can either be user software interrupt, supervisor, hypervisor, machine. So of course for us, we're in machine mode all the time because we're on bare metal. We're not doing any like user level or supervisor stuff. You'd be doing that kind of thing if you're on Linux, of course. Linux would be using like supervisor and your software would be running as user. But like I say, we're bare metal, so we'd expect exception code 3 for machine software interrupt, or 7 for timer interrupt, and external interrupts would be 11 for us. And then here's what I was talking about how it could be like hardware exceptions. So you could have a misaligned instruction address. an instruction access fault, an illegal instruction, a breakpoint. So that would be useful for a debugger. If you're setting breakpoints in a debugger, you can actually trigger and interrupt one of these kind of exception interrupts. Load address misaligned, load access fault, store/AMO address misaligned, store/AMO access fault, and environment calls as well from USHRM modes, and then the rest of them are reserved, of course. So those are the different kinds of interrupts we can detect with the mcause register. And so I'm pretty sure the CSRR instruction is just passing the entire contents of mcause, just reading it into A0, and we're passing that into handle trap, which makes sense. So let's see the CSRR instruction. Let me see here. I wonder if the actual instructions are in the user documents. I think that might be the case. Okay, so that would probably be in the I instructions, at the base ISA, right? Control and status register instructions, yeah. So CSRR is going to be, is that a pseudo instruction? That might be one of the pseudo instructions, because we have RRW, RRS, RRC, RRWI, RRSI, RRCI. So there's not just an RR, CSRR. Control status register read is what we're looking for. I'm pretty sure that is one of these pseudo instructions. Yeah, the assembler pseudo instruction to read a CSRR, is encoded as CSRRS, where we're using the X0 for the store portion. And this is something we saw very early on when we were studying this stuff. Somewhere up here. Yeah, right here. So we see we already studied this. So then CSRRS reads the value, writes it to integer register RD. It's 0 extended, of course, to excellent bits. The initial value is treated as a bit mask that specifies bit positions to set in the CSR. Of course, we're passing X0, and that means we're not setting anything, we're just reading. That's what the pseudo instruction does. So yeah, we're just reading mcause into A0, like I said, and the same with mepc to A1. So that's telling us where the exception happened. This is telling us what kind of interrupt it is, whether it's like an exception kind or whether it's like an interrupt kind. I don't really know what to call those. But the two different types that you can have. And it also has the field, the part of the register that indicates the code, the exception code. So you can get more specific information about what caused the interrupt that way. And then we're putting the stack pointer at A2, and then we call handle trap. So what's the point of putting the stack pointer in A2 though? I'm not sure exactly why you'd want to pass the stack pointer in as an argument. Yeah, I'm not sure why you would do that, but these two make sense, right? If you're doing a trap handler, you'd want to know those. Okay, now A0. So that's not the return address. But is it... Do we pass the return through A0 is what I'm wondering. I think you would... The return value of the function would be passed in A0, I'm pretty sure. Yeah, it says right here. The first two of which are also used to return values. So A0 is the return value. And of course in C we only have a single return, so I don't think you'd ever use A1. Maybe I'm wrong about that. I don't know when you would use A1 if you're writing C code, but I suppose it would matter in other languages. Okay, so we know what's going on here. I don't understand the reason behind this particular line, but I'm sure we'll figure it out. We call the trap handler, and then the return value of the trap handler, we're doing a CSRW mepc. So mepc was the program counter when the exception occurred. So it looks like we're writing the return value into mepc. I don't understand exactly why we would do that. So let me see here. So first of all, CSRRW is what we're using, right? CSRW, so that must be a pseudo instruction for just writing. Yep. CSRW is encoded as CSRRW, X0, CSRRS1. So now let's take a look at this one. It atomically swaps values in the CSRs and integer registers. Reads the old value of the CSR, 0 extends the value, then writes it to integer register RD. The initial value in RS1 is written to the CSR. If RD equals 0, then the instruction shall not read the CSR and shall not cause any of the side effects that might occur on a CSR read. So that's what we're doing. We're setting RD to 0. So we're just writing the value in RS1 to the CSR in RD. So yeah, we're just writing the value in A0 into mepc. So I don't understand why you would overwrite mepc after you've done your handler. That's my other question of the day. mepc, the machine exception program counter. So yeah, it just says that when a trap is taken, mepc is written with the virtual address of the instruction that encountered the exception. Well, let's take a look at a handler written in C and see if we can relate what we're doing in C code back to what we're doing in the entry.S file. So I want to take a look at init.c because init.c has a good interrupt handler. To study from. Okay, so handle trap, we see we're defining it to take mcause and EPC. We're not defining it to take the stack pointer, interestingly, but it is being passed. It's just not in our function signature. So we're just not using that argument that's being. So that might be a thing to ask on the big risky business question thread. Why we write the stack pointer into A2. But yeah, let's read this code here and see what all it's doing. So this is commented out with an if 0. But we have if mcause is mcause interrupt and mcause cause is irqm external, so this is an external interrupt. Then it calls handle external interrupt. Here we're saying if it's an interrupt and the cause is timer, then we do a timer interrupt. Else we write, so this is the case where it's like a an exception, a hardware exception, or like a software breakpoint, things like that. We write trap and we exit with 1 plus mcause. Otherwise, we return EPC. So we're just returning EPC, and that's getting written back into mepc. So I guess I have two questions about about how entry.s is working. Why we're doing this move and why we're doing this write. So I understand that this is the return value from the handle trap, and I understand that we're writing it into mepc. I just don't understand why we're doing that. And I don't understand why we're passing the stack pointer and is A2. So let's go to the big risky business question thread. Do I have that open? Okay. So let's head over to the SiFive forums. Now, did I put that under -1? I don't remember where I put that. Yes, I did. Big risky business question thread. So let's write a new reply. I should probably wait to post this until we actually have read the rest of it, because I might have more questions as we continue to read. But this is the part that I have 2 questions about. Here, let's paste the code in. That's not what I wanted. Try that again. That's doing the same. I thought I hit in the wrong key or something. There we go. Must have just been hitting the wrong key. And we are going to indent that so it's code. Why do we move A2 SP? I don't understand the purpose of passing the stack pointer as a third argument to the trap handler and the interrupt, well, trap handler would be the better term, because we delegate to interrupt handlers for each specific interrupt. So I think that's the best terminology there. So, yeah, the Freedom E SDK doesn't use it in init.c. And the other question, I guess, is why why do we do CSRW mepc A0? I understand that A0 is the return value of the trap handler, but I don't understand why we'd write it back to mepc. Isn't mepc just to tell us what instruction caused the trap? Okay, so I think that's good, but let's continue reading the code. So we do li mstatus mpp to t0. So t0 would be a temporary, right? Temporary registers, yeah. And li, what is the li instruction? So let's see if we can find it here. Let me take a look at my green card. So I'm not seeing it here, but I think it's going to be a load immediate of some kind. Like there's LUI, which is load upper immediate, for example. I feel like li is probably a pseudo instruction. For some kind of load. Yep. So here's a list of pseudo instructions. One of them is li, which is load immediate. So we're loading an immediate value into t0 is what we're doing. So if we look at load and store instructions, where does it list? So I'm not seeing the documentation for this pseudo instruction here. But my green card had it, that it's a pseudo instruction. Does it say what it's a pseudo instruction for? Okay, yeah, this says what it's for. It says RRD equals immediate. So I don't know, maybe I'm just failing to see it in my skimming here. I wish this search would let you refine it to not include like things that are subsets of a word. You know, like I just want li specifically. Well, whatever. We know what it does. I mean, it's pretty obvious. It's loading the immediate into the register. So we might come back to looking for it in the documentation at some point, because being able to find things in the documentation is important, of course. But so it's loading MSTATUS MPP into T0, and then it's doing a CSRS. So that would be a pseudo instruction for a store, probably a CSRRS, T0 MSTATUS. So we're storing the MSTATUS MPP into MSTATUS, basically. I think that's what we're doing. So I think effectively this is setting a bit or a few bits, because this has got to be a mask, right? And we're setting those bits in MSTATUS. So let's find MSTATUS in here. So it looks like it has a lot of documentation. Here's the layout. So I think what we're doing is we're setting bits in the MPP field, because it was MSTATUS MPP, the immediate. And we see MPP right here. So let's go back to the CSR instructions. Okay, set and clear bits in the CSR. So CSRS. Oh, it uses CSRSI. That makes sense because it's an immediate. So yeah, they update the CSR using an immediate, basically. So that's pretty straightforward. And we're setting the bits in MSTATUS using MSTATUS MPP. Interestingly, though, so this is using a CSR SI instruction. Or wait, no, never mind. The CSR SI instruction would be the pseudo instruction to use an immediate. So MSTATUS MPP might not fit in the immediate, so we're storing it to a register and then using CSRS instead of CSRSI. I think that's the logic there, that presumably it wouldn't fit in the immediate, so we put it in a register and use CSRS. That would be my assumption on why we're doing it this way. So the question is, what is MSTATUS MPP? And presumably, that's going to be defined in encoding.h or in SiFive bits.h. Let's check encoding.h first. And we just happened to hit it right away, MSTATUS MPP. So it's 0001800. Okay, so this is what 1800 is in binary. So here's a nibble. Here's the nibble. And then the high bit is set in this one, which is why this is an 8. And then the low bit is set in the next one, which is why this is a 1. Right, so that makes sense. And so we're setting 2 bits, basically, with this instruction. And I'm guessing those bits correspond to the bits in the MPP field. So we see here's a nibble. Here's a nibble. And then this one would be 0. This one would be 0. This one would be 0. But 12 we would be setting, right? Shouldn't we be setting 11 and 12? I think we're setting the 2 bits of MPP. So, right, there'd be 1 nibble, 2 nibble, 3 zeros, and then 2 ones, right? So let me check this again. One nibble would be these. Oh wait, here's what I did wrong. 1 nibble, right? I was off by 1. This is 4 bits right here. So there's another 4 bits. 1, 2, 3. Yeah, so we're setting bits 11 and 12, the MPP field. So let's take a look at the MPP field. Okay, here we go. Memory privilege in MSTATUS register. MPRV bit. Wait a minute. Is MPRV... MPRV must be one of the MPP bits, right? Or wait... No, MPRV is up here. I care about the MPP bits. Let's see here. When MPRV equals 1, data memory addresses are translated and protected as though the current privilege mode were set to MPP. MPRV bit modifies the privilege level at which loads and stores execute. Okay. So MPP is setting the privilege mode for loads and stores when MPRV equals 1. The MPRV and MXR mechanisms were conceived to improve the efficiency of M-mode routines that emulate missing hardware features. For example, misaligned loads and stores. MPRV obviates the need to perform address translation in software. MXR allows instruction words to be loaded from pages marked execute only. So what are the different values for MPP though? I mean, presumably we're setting it to M. We're setting both bits. And it says remain in M mode after MRET. So earlier I actually watched the webinar SiFive webinar. I signed up to attend this, but then I slept through it. But they put the videos okay, here we go. I should put this on the links.risky.tv. I probably will do that at some point. But yeah. So there's part 1, RISC-V 101, and this is the one that I signed up to attend, but then I slept through it. And then part 2 has happened as well, and I don't think I even signed up for that one because I missed the first one, and I knew I'd probably miss the second one if I signed up anyway. So, but it's great that they put the videos up so you can still watch them even if you miss them. So there's a full webinar recording for the first one that I watched earlier, and I remember they said that like I think when you do a call, it saves the context of the state of the machine. So the privileged mode you're currently in gets saved to MPP when you do a call, and when you return, it writes it back out to from MPP to the current privilege mode. I think something like that is how it happens. So I think what we're doing is we're just ensuring that when we do the MRET from this entry.S, that we remain in M mode. We remain in machine mode. but where would we actually find that in the documentation that it does that? I suppose that's like an ABI thing, so maybe let's go back to the ABI documents. But yeah, if you watch that webinar, you'll see what I'm talking about. But I want to know where it's actually defined in the specs. So it might not be in here. Just skimming over it, I didn't see it in the ABI documents. Let me search MPP and see where all it turns up in this document. Here we go. When a trap is delegated to a less privileged mode, the mcause register is written with the trap cause, the EPC register with the address of the instruction that took the trap, the XPP of MSTATUS is written with the active privilege mode at the time of the trap. The PIE field of MSTATUS is written with the value of the active interrupt enable bit. And the IE of MSTATUS is cleared for the privilege mode that we're talking about. The mcause and mepc registers and the MPP and MPIE fields of MSTATUS are not written. So that's not exactly what I was looking for. Physical memory protection. Oh, so that's when you're using the MPRV bit. So that's not what I was thinking. Here we go. The MRET instructions are used to return from traps in M mode. When executing an MRET instruction, supposing MPP holds the value Y, and we're going to say Y is M because that's what we're setting it to. And again, we didn't see where it actually defines that M is both bits set, but it's obvious from what they're talking about here, about how UPP would be 0, SPP would be 1 bit wide. So that would mean that 1 would be S supervisor. HPP is 2 bits wide, so 2 would be hypervisor, and then MPP is also 2 bits wide. So if you set 3, which is 1 1 in binary, then that would be the machine mode, right? So they didn't explicitly list it, but you can derive it just from understanding the different widths of the different PP fields. So I'm quite confident that it's machine mode, and like I say, the comment says that it's machine mode as well. But again, that's another thing that would be useful to find in the document. Oh, here we go. So again, this isn't explicitly saying it, but it's saying 0 0 or 1 1 if it's U or M. If only M, then it's hardwired to 1 1. So that confirms what we thought. I'm surprised they didn't list it in a table. Maybe it's listed in a table somewhere else in the documents. But we figured out what we needed, nonetheless. So if we're saying y is m, MIE is set to XPIE. So what was X in our case? So X is M in our case as well, right? We're assuming we're in, we're talking about MPP, right? We are talking about MPP in the MSTATUS register. So supposing MPP holds the value y, and we're saying y is m, so we're staying in machine mode. MIE is set to MPIE. The privilege mode is changed to M. MPIE is set to 1, and MPP is set to U or M if user mode is not supported. So it sets us to machine mode, but the MPP gets cleared out to 0. So that's interesting, actually. When the stack is popped, the lowest supported privilege mode with interrupts enabled is added to the bottom of the stack to help catch errors that cause invalid entries to be popped off the stack. So when we enter the interrupt handler, are we actually dropped into user mode instead of machine mode if we support user mode? Is that what that's saying? I'm not totally sure if that's how it works or not. I thought we stayed in machine mode. So what I'm wondering, I guess, is when we take an interrupt, do we swap the value in MPP with the privilege mode, or do we just store the current privilege mode into MPP? Because if we swap it, and we're saying after an MRET it's set to U, then that would put us in user mode when we enter the trap handler. but I'm not sure if that's how it works or not. I'm gonna assume for now that we stay in machine mode, but that's something to keep in the back of our minds. I'm sure we'll get a deeper understanding of this at some point. But for now, I think we're just gonna assume we're staying in machine mode and keep reading the code. So this is just setting it up so that we make sure we stay in machine mode after the MRET instruction. So I wonder why we would need to do that. I suppose maybe when we do a call to handle trap, it's possible for it to switch the mode. I'm thinking that might be why. That it would be possible for it to switch the mode when we call handle trap and then leave it after you return from handle trap. I'm not totally sure. Well, I mean, yeah, if we set MPP to be like user mode, and then we do MRET from the routine that we call, then it would put us into user mode at this point. So this is just making sure we stay in machine mode after we return from this routine. So yeah, then we restore our registers. We deallocate the memory that we were using to store the registers on the stack, and we do an MRET. So let's see documentation for the MRET instruction. Where would that be? You'd think it would be, the actual instruction would be in here somewhere, right? In the user level ISA. Let's see. I wonder, would that be considered environment call and breakpoints or control transfer? Let's search MRETs. I didn't find it. RETs? So it might not be defined in this document, actually. Well, here we're talking about ABI. Okay, so here 20.2 RBG calling convention has ABI stuff in it in the user document. So that's good to know. Okay, so it says ret is a pseudo instruction, but is that true for MRET? This is just RET. I'm looking for MRET specifically. I think that might be different. Because RET is just a pseudo instruction, right? It's just a jump. A jump and link registry. So let's search MRET in this document, the privileged architecture. Oh, what did I do now? MRET. Okay. So it does have it in this document. It's the trap return instruction for machine mode. So an XRET instruction can be executed in privilege mode X or higher. So you'd have to be in machine mode to execute MRET. Right, but the MPP could be set to user mode because that's not the current mode you're in. So that makes sense. And so I think I'm right that we are always in machine mode when we take this trap handler. So XRET instructions will pop the relevant lower privilege interrupt enable and privilege mode stack. In addition to manipulating the privilege stack, as described in section 3.1.7, XRET sets the PC to the value stored in the XEPC register. Okay. So when we're setting MEPC, the MRET is going to set that to the PC. So when we return from this trap handler, we can actually specify from the handler that we write, the return value, we can actually specify where we want to actually return to. So rather than returning to where we were when we took the trap, we could actually set it to return somewhere else, because this is going to set the PC. So that kind of answers one of my questions. I'm still going to post the question on the forum just to see what other people say about it. But I think that kind of answers one of my questions. That the reason we're setting MEPC with the return value is because when we do the MRET, that's going to set the PC to whatever we put in it. Interesting. So I think I'm following that now. And with that, I guess the only other questions are regarding the GNU assembler syntax for the surrounding stuff, like the .weak handle trap 1:J1B. I take it this is just a stub. For handle trap, and the section text entry aligned to global trap entry stuff is the other thing I'm not totally sure about, and we'd have to check the GNU assembler syntax stuff, which again, under links.risky.tv, there's a GNU assembler syntax manual. So the GNU assembler manual using AS, which is the GNU assembler. Or I guess just the generic name for the assembler command. But we might take a look at this in more detail a different day, because I know we've been streaming for a while. I forgot to do the start thing that I normally do. I shouldn't have done that, but it looks like I started streaming around 1446, and it's around 1616 now. So that is longer than a normal stream, I guess. Not by too much, though. But yeah, I might end it here. I'm just curious, before I stop streaming. Here's a .weak, that's what I was wondering. This directive sets the weak attribute on the comma-rated separated list of symbol names. So it creates symbols. So it's putting symbols in an object file, basically. So this is something where I just don't know a lot about this stuff. About like object files and executable formats and things like this. What it means to have the weak attribute on a symbol name. Weak symbol. So Wikipedia's got a page on it. A weak symbol denotes a specially annotated symbol during linking of an ELF object file. So presumably, when we compile with GCC, it creates ELF object files, but after linking, I assume that the linker is being instructed with like the linking scripts, like the linker.lds and whatever. I assume it's being specified to write out like an executable that's just designed to run on bare metal, not like an ELF file. But the intermediate object files would be ELF, since we're using the GCC toolchain. That kind of makes sense, right? But so a weak symbol, by default, a symbol is strong, whatever that means. During linking, a strong symbol can override a weak symbol. Okay, so yeah, that makes sense. we're saying we have the symbol handle trap, but this is a weak symbol. So if you define handle trap in another file, which is what we do, we define our handle trap, that's going to override this one. So this is just a stub, like I thought. Anyway, we're going to continue studying this another day. But thank you everyone who tuned in, if anybody did tune in. No chat today, but like I say, I haven't streamed in a while, and I haven't been being regular about streaming. I did have a canker sore last week, and then I didn't stream Monday, but I want to get a lot of streams in here at the end of October, because we haven't had many Risky Business streams this month, and we need to correct that. We need to have a lot of Risky Business streams. But yeah, thank you everyone who watched, and thank you everyone who watches on the YouTube archive, which is available at risky.tv. You can follow me at HMN_risky on Twitter to get updates about this series. I'll try to start tweeting out again when I stream, and maybe even get a schedule going again. I'm still trying to figure out the ideal sleep schedule for me. I don't really know yet. I've been trying to sleep from like noon to like 8 in the afternoon, and then be awake the rest of the day, but that hasn't really been working for me lately. I've been trying to do that, and I find that during the afternoon I can't really get to sleep, and then I just end up sleeping later on and sleeping later than I intended to. But I ended up waking up around noon today. I was trying to sleep a little bit earlier than that, and I ended up waking up, and I was like, I feel like doing some Risky Business streaming. So maybe this is a good time for me to be awake. This is when I used to stream. And it seems to work out for me. So we might go back to that kind of schedule. And then also, thank you everyone who supports me on Patreon. That makes the series possible. And I think I have some new patrons to shout out. I think there's one new patron. Let me see. I need to sign in. Just a moment. Must be my other email. I have 2 email accounts, so yes, I am not a robot. Log in. There we go. Yeah, okay. Thank you, DannyFritz, for the pledge. I appreciate it. And if you would like to support me on Patreon, you can do so at patreon.risky.tv. I will see you guys in the next episode, and stay risky, everyone.